Now let's look at what is latent heat and specific latent heat. Remember, if we were to heat up the solid at this point here, it will melt at constant temperature. So the amount of heat that we supply in this region will be used to calculate the latent heat. So latent heat is just the amount of heat energy that you supply from here to here. That means the total heat supplied to change the phase of the solid to liquid at constant temperature. And latent heat of this is called the latent heat of fusion. And for this side, if we were to heat up the liquid and it becomes gas at constant temperature, then the amount of heat that we supply is called the latent heat of vaporization. So latent heat of fusion and latent heat of vaporization we call it are reversible. That means whatever heat that you supply for your solid to become liquid would also be the amount of heat released for the liquid to become back solid. Alright, so it's reversible. So again, the amount of heat that we supply here, if we divide by the mass, then we will get specific latent heat of fusion. And the heat supplied here, we divide by the mass, we get specific latent heat of vaporization. So if we look at what is just latent heat, so latent heat is just latent heat of fusion is just the heat energy needed by a solid when it undergoes a solid to liquid phase change at constant temperature. Whereas latent heat of vaporization is the heat absorbed to cause a given liquid to undergo liquid to vapor phase change at its constant boiling point. But latent heat by itself is not very useful because it also depends on the mass of the water becoming steam or the mass of the solid becoming liquid. So latent heat wouldn't be concerned about the mass. But if you want something more useful, something that tells us a property of the material, we use specific latent heat. So specific latent heat is the heat energy needed per unit mass required to change the phase of substance from solid to liquid at constant temperature. And specific latent heat vaporization is the heat energy per unit mass required to change the phase of the substance from liquid to gas at constant temperature. So you look at the formula, latent heat is just Q, whereas specific latent heat is Q over M. Now, between these two, which is specific latent heat of fusion and specific latent heat of vaporization, which one is bigger? Which one do you think? The amount of heat needed to melt ice at zero to become water at zero, or the amount of heat energy needed to change water at 100 to steam at 100? The answer is specific latent heat of vaporization is always bigger than specific latent heat of fusion. The reason is in vaporization, the change in volume is extremely big. Compared to melting, because if you remember the first part of the chapter, we said that the spacing in solids and liquids are almost the same. So during melting, the change in volume is actually very small. Most people even consider it negligible. So therefore, the change in PE is not so great. But if you look at vaporization, when liquid becomes gas, the change in volume is very, very big. So which means to say there's a bigger increase in separation, so PE increases. That's the first part. And then the second part is because when the liquid tries to expand into a very big volume, it has to push back the atmosphere. So there's also external work done against atmospheric pressure. All right. So these two are the main reasons why your specific latent heat of vaporization is bigger than your specific latent heat of fusion. So let's look at the experiment in order to determine the specific latent heat of vaporization. So please remember this experiment as well, as this is also compulsory. So remember the formula that we talked about just now for specific latent heat is Q divided by M. So notice there's no theta there because there's no temperature change. It's supposed to happen at constant temperature. Now, determining the Q is not a problem. We have examined it in the previous two experiments where we just have to use an electrical heater. Alright, and you see the circuit diagram here is the same, so we can still use VIT. Now, the only problem for us is to find the mass, because this M actually represents the mass of, in this case, mass of water that becomes steam at constant temperature. But how are we supposed to calculate that amount of mass precisely? or accurately. Because if you were to start off with water at room temperature, and as you heat it up, some water will start to evaporate, but then you cannot consider that mass. You can only start to measure the mass of the water that becomes steam when the water has reached 100 degrees Celsius. So what some students say is that, oh, you can just weigh the water here before and then weigh it after, then we subtract to get the mass of water that has become steam. So that is not accurate, because during the process of heating this water, before it reaches the steam point, some water would have already evaporated. So how do we calculate accurately? So let's look at the setup here. Here, when we boil the water will turn to steam and it will escape from these two holes here. It enters into the condenser, and then the water will accumulate at the beaker here. So what we will do is we will first heat up the water here. Notice we don't need a stirrer, because when the water boils, it already agitates on its own, so we don't have to stir it. So what will happen is as the steam starts to move up, we don't care. We just ignore whatever water that is collected here. So we wait for a little while until the temperature of every part of this apparatus becomes constant. Now, I'm not saying the temperature here is the same as temperature here, is the same as temperature here. Of course, they are different, because the nearer to the steam, the hotter it is. But what I'm trying to say is the temperature of this part becomes constant, and the temperature of this part becomes constant, and this part becomes constant, then we are good to go. But there's a better way to test whether or not the boiling is happening at constant rate. So what we do is then we start collecting the water here for a specific time interval, let's say 5 minutes. So we collect the water here in the beaker for 5 minutes, and then we weigh the water here. How? By weighing the empty beaker and then weighing the beaker with the water and subtracting to get the mass of water inside here. So after 5 minutes, let's say you're getting 20 grams. All right, then you throw the water away, and then you put it back in underneath and collect for another 5 minutes. Now let's say now instead of getting 20 grams, you're getting 30 grams. So which means to say the boiling is not stable yet. So we keep doing this. That means we keep collecting water for 5 minutes until the mass of water that you collect for that 5 minutes becomes constant. So let's say 40 grams. So every time you collect water for 5 minutes, you're getting a constant value of 40 grams. Now that will be the mass that we use here. So why do we use that mass here? Because when the mass of water that you collect here becomes constant, it means that the rate of water boiling to become steam is equal to the rate of the steam condensing to become water. So whatever water that we collect here for 5 minutes would have been the amount of steam that condenses to become water in 5 minutes, but that is also the amount of water turning into steam at only for 5 minutes. So do you know, remember the formula QVIT? So the T we will use 5 minutes, and the mass here we will use that constant mass, which is 40 grams. So that's how we calculate the specific latent vaporization. So what about the formula? So if we see that the formula would become energy supplied by the heater is equals to heat gained by the liquid to vaporize plus heat loss. So we have VIT equals to ml plus H. But you notice that we did not wrap the apparatus with insulation. Is it because there's no heat loss? Actually no, there's actually even more heat loss because the temperature is even higher. But why don't we wrap with thick insulation? Because we realize that in this experiment it is possible for us to totally eliminate heat loss from the calculation, not just assume that it doesn't exist and give you an inaccurate answer like previously for specific capacity, but this time we can totally eliminate it from the equation and we'll get a totally accurate value for specific latent heat. So how do we do it? Now imagine that the first set of data you use a low voltage and low current, but we collect water for 5 minutes and let's say we get 40 grams. All right, that is my first equation. Now I repeat the experiment, but this time I use a higher voltage, higher current. So obviously the heater is hotter, so more water boils off. So instead of getting M2 or 40 grams, I will get something higher, let's say 70 grams. So I'll get a higher mass, but don't forget to collect water over the same time, which is also 5 minutes. The T here and the T here must be the same, but different voltage, different current will give you different mass. So the question is, why do we do twice? Because the heat loss here and the heat loss here are exactly the same. How can it be? Because your heat loss here and here, which is the heat loss from the apparatus to the surrounding, depends on two factors. One is exposure time, how long you allow the heat to transfer. Another one is the temperature difference between the apparatus and the surrounding. So do you realize that for both these cases, even though you're using low heater power, high heater power, but the temperature of the apparatus, which is boiling water, is still 100 degrees. So there's the same temperature difference with the surrounding, and we are collecting water over the same 5 minutes, so this is the same exposure time. So therefore the heat loss in both these two equations are exactly the same. So what can we do? We can solve simultaneously. We take equation 2, subtract with equation 1, the h will disappear. And then what we'll have is a combined equation here. So if we use both sets of values of V and I, both sets of values of M, we will be able to get the accurate value for specific latent heat of vaporization. So then some students ask me, why didn't I do the same thing when I wanted to determine the specific heat capacity? Why couldn't I do twice and then subtract to get rid of the heat loss? It's because in specific to determine specific heat capacity, if you use different heater powers, the temperature rise won't be the same. So therefore, there's a difference in the temperature difference between the apparatus and the surrounding. So you won't get the same H if you're doing it for a specific heat capacity, because you use higher voltage and higher current, the temperature rise will be bigger. So that means the temperature difference with the surrounding is bigger, so you get a greater heat loss. All right, so we can only use this to determine the specific latent heat of vaporization.